Okay, I'd like to welcome everyone to our presentation. And I almost said this evening, but I looked at the registration list before we got started, and I think we've covered every U.S. call area, most of Canada. We've got friends in Europe that have registered, Mexico, Brazil, a couple of people over in India. So we've had quite a wide reach as far as the registration goes, and we're glad people could join us for this presentation. I think for most of you, Carl probably doesn't require much of an introduction. He's very well known from his articles in NCJ and presentations at Dayton, Visalia, and so on. Carl does hold a Master of Science in Electrical Engineering from Purdue, and as most of you know, he enjoys DXing, contesting, experimenting with antennas, and trying to understand the physics of propagation, which is what he's going to share with us in this presentation. Also, I think many of you probably know his wife, Vicki, Alpha Echo 9 Yankee Lima, and the two of them enjoy traveling and operating from abroad, places like Syria and Market Reef. And I forgot to ask you, Carl, I think she didn't go along to Market Reef, did she? Or?
Oh, yeah, sure did.
Oh, she did? Okay.
Yeah, she was, in fact, she wasn't the first YL that ever operated there. I think back in the 70s there was a German lady who made a few contacts.
I'll be darned. Okay.
She was there to make lots of contacts, and we were there, I think, 3 days, and yeah, she had her own rig, and that was it.
You know, now that you say that, I think I do recall that. That's pretty good. Okay. Well, and also if you get to some of the conventions, you're likely to find Carl checking cards for the DXCC program, and he especially enjoys the older cards and the deleted entities. So with that, Carl, the floor is yours, and take it away.
Okay. Well, thank you, Ken, and hello to everyone. Good morning, good evening, whatever, good afternoon. As Ken said, it looks like there's a pretty good international crowd here this evening. So what I'm going to talk about is disturbances to propagation. And kind of little summary of that is calling CQDX and then asking, okay, where'd everybody go? Sometimes that happens. So what we're going to try and do is take a look at the various disturbances, look at some logs. Hopefully you'll come away with a little better picture of disturbances to propagation. And again, it doesn't advance. There it is. Okay, so there's the agenda. We'll take a real quick look at the recent Cycle 24 activity. I believe there's some good news coming here. We'll look at the WWV format and the Space Weather Prediction Center homepage in relation to disturbances. Take a big picture look at it. Then we'll get into some detail by showing their impact to real-world operating. And what I've done is got some basically contest logs to look at the various disturbances and how they impacted them. Contest logs are very good tools to better understand propagation. Then kind of as a bonus, we'll take a look at the auroral oval images that are very widespread. There is some misconception on those, so I thought I'd briefly explain those. And I'm not sure Ken mentioned it, but I'll mention it, that this presentation will be on the PVRC website, which is at that URL there. So if you need to come back and look at it again or tell your friends about it, whatever. I think Ken and the crew are doing a heck of a job with these PVRC webinars, and hope to see a lot more different type topics in the future. Okay, a quick look at recent Cycle 24 activity. Well, the big news was Region 1029. It rotated into view on October 23rd, and it became the biggest active region of the year. That's why there's a smiley face there. It produced 10 Class C solar flares during a 3-day period, actually 4-day period, and that more than tripled the number of C-class flares that previously had been detected in all of 2009, so that was kind of interesting. It certainly helped 15 meters for CQ Worldwide phone. From our house here in northeast Indiana in Fort Wayne, we did a multi-2 operation, mostly a have fun and introduce hams to DX contesting, and I think we did very well in accomplishing those goals. We worked 91 countries on 15 meters, which isn't too bad for solar minimum. Now this region rotated out of view on October 31st, so it was there and it gave us some good activity. And here's a quick little picture of what it did for us. This is the Millstone Hill ionosonde in Massachusetts, and what's plotted is every day of the month for October, and the vertical axis is the 3,000 kilometer muff that assumes a 3,000 kilometer path with the center over Millstone Hill, and it's the F2 muff. I've also included a 15-meter line and also a 10-meter line so you can more easily see what was happening each day compared to those two bands. You can see up until region 1029 rotated into view, that 15 meters was kind of iffy, at least for those of us in the Midwest. This ionosonde is kind of nicely situated in that it's along the path to Europe, so what it's doing can give us, those of us in the Midwest, a good indication what may happen to the bands. If worldwide phone would have been held on October 9th and 10th, you can see that it doesn't look like 15 meters would have been very productive to Europe. But fortunately, it was held on the 24th and 25th, and you can see there's a good general uptick in the muff when region 1029 rotated into view. And in fact, a couple days after worldwide phone, the muff was even higher, probably some good 12-meter openings if I remember correctly. So I just want to thank the sun for region 1029. It really helped us a lot. And I know that Europe had lots of good 15-meter openings. They also had a lot of good 10-meter openings. And looking at some ionosonde data in Europe shows that it looks like it was a lot of F2 over there in Europe. So I think this is just a hint of what's to come here. Okay, this is the positive graph. Finally, it says things may be picking up. The plot shows 4 years of data by month. It's the monthly mean sunspot number. In red are those sunspots that were associated with cycle 23. In blue, the sunspots associated with cycle 24. And I'll just point out that for about a year and a half, both cycles overlapped. We saw cycle 23 spots concurrent with cycle 24 spots. That's typical. Nothing to get worried about. Now you can see that the blue vertical bars seem to be picking up. In fact, in September, the monthly mean sunspot number was about 6. In October, it was 7. And so far in November, it's 4.4, and we're just a little bit half over with November. So things are looking pretty good. If you look at the smooth sunspot number, which is the average 12-month running average of the monthly means, you'll see that it minimized in December 08, which is the current NOAA prediction for sunspot minimum. So things seem to be following the predictions that are out there at the moment by NOAA, and that's encouraging. The March 09 smooth sunspot number will be available when we get the November 09 monthly mean data, which is about 2 weeks away or so. Hopefully it'll be a little bit higher than April, in fact. So a little summary here on some of the active regions. 1029 actually persisted. It came around again, and it rotated into view on November 14th, but it seemed to have fizzled out. That's why the unhappy face there. But fortunately, there's been some other regions that have been producing some activity. Region 1030, 1031, and right now there were 2 regions that were named yesterday, or numbered yesterday, 1032 and 1033, and they're producing more sunspots. So hopefully this activity will continue so that the November 2009 monthly mean will be higher than the October, and of course that'll mean the March smooth sunspot number will be higher than the April, which means in general there's an uptick in activity, and it appears maybe that the sun is finally starting to wake up. Now, the result of all this increased solar activity, of course, is more disturbances to propagation, and that's the topic for tonight's discussion. Okay, let's take a look at the WWV format. and also the Space Weather Prediction Center homepage. Back in March of 2002, the WWV format changed. It currently has 3 sections. It gives the current indices, a summary of the past 24 hours, and a forecast for the next 24 hours. Now what changed was the reporting of specific disturbances to propagation. This was much better spelled out on what effect the sun has on our terrestrial environment. And here's a sample report. Again, the top 3 lines are for the current, the next 4 lines are for the past, and the bottom 3 lines are for the next 24 hours. What I've highlighted in red are G's, S's, and R's, and that's what we're going to talk about, and that's what the change was in the WWV reports. They got very specific about the different kinds of disturbances to propagation. Now you can see this also on the Space Weather Prediction Center homepage. It's at that URL there. And what they do is give a past 24 hours and the current. And at least on the day that I picked this up, which was, well, it was recent, there was no storms of any kind. And currently there weren't any, and the past 24 hours there weren't any. But as soon as cycle 24 starts really getting up there, we're going to see a lot more activity. So what does GSR refer to? Well, G refers to geomagnetic storms. They're caused by gusts in the solar wind from coronal mass ejections or from high-speed streams from coronal holes. And they can cause auroral absorption, auroral E, and depleted F region ionization. S refers to solar radiation storms. That is caused by energetic protons from big solar flares. Not all solar flares emit energetic protons. Some do, and what they do is can cause an increase in D region absorption in the polar cap, and this is called a polar cap absorption event, a PCA. The R refers to radio blackouts, and this is the electromagnetic radiation from big solar flares, generally of X or M class. Solar flares are classified B as small, C is next, M is next, and X is the biggest. So when we get some big M class flares or X class flares, there's a likelihood that we'll have some radio blackouts. And what it does is causes D region absorption on the daylight side of the Earth. Now for all 3 of those disturbances, the scale is 1 to 5 as reported by WWV or on that SWPC website. 1 is minor and 5 is extreme, and they correspond to specific criteria, which all the details of that are at that URL. Okay, the big picture. What we're looking at is we're looking down on the Earth on the northern hemisphere, and you can see that there is a day-night, a terminator line there going from basically the southwest up to the northeast. The X marks the spot of the north magnetic pole. That's what the auroral oval is centered on. And you can see there was some good auroral activity for that night. Now we'll start with geomagnetic storms. What they can do is depress the F region muffs at high and mid latitudes both day and night. And that's what those 2 arrows show. Geomagnetic storms can also cause auroral absorption and auroral ionization. And that is, of course, a very aptly depicted in the reddish areas there in the auroral oval of this picture. That takes care of the G. The S is solar radiation storms. Those are protons from solar flare, and they cause absorption in the polar cap. The polar cap is that area within the auroral oval, and of course it's also centered on the magnetic pole. And the last one is GSR. R is the last one. That's the radio blackouts, and of course it causes absorption, but only on the daylight side of the Earth. So there's a good overall picture of the three disturbances to propagation and what part of the Earth that they affect. Generally, they don't have too much effect at low latitudes in the equatorial regions. And of course, generally, what happens up in the northern hemisphere at the high latitudes also happens at the high southern latitudes, at the Aurora Australis, I guess it's called, or if I pronounced it correctly, the southern auroral oval. Okay, let's go through some of the impact to real-world operating. So what we're going to do first is track a geomagnetic storm and look at W4ZV contest log. Okay, what we're going to start with is a coronal mass ejection that was seen by the coronagraph on LASCO, which the acronym is spelled out there, which is on the SOHO satellite, which is the Solar and Heliospheric Observatory. What the coronagraph is basically a telescope with an occulting disk to block out the main body of the sun. What that allows you to see is stuff coming off the sun when disturbances happen. Now this CME occurred at 0342 UTC on May 22nd in 2002. The picture shows what the coronagraph saw. And this was a halo event. The halo means the CME explosion is seen all around the disk, the occulting disk, and that indicates that the CME is headed towards Earth. So a CME occurred at 0342 on May 22nd. And now we look at, on the right, the Advanced Composition Explorer satellite. It's about 1 million miles from Earth on the line from the Earth to the Sun. The shock wave took about 30 hours to get to the ACE satellite. Since it's 1 million miles from the Sun, that leaves about 92 million miles from the Sun to the ACE satellite. And it did it in about 30 hours, so that means the speed was about 532 kilometers per second. And the result of that is those dials you see. The dials are at the Space Weather Prediction Center homepage also in the Space Weather Now link. And what happened is when that CME hit the ACE satellite, the interplanetary magnetic field turned south, which usually means trouble. Since the speed was up at 532 kilometers per second, that's what registered on the little speed dial. Normally, the solar wind is about 400 kilometers per second. And the dynamic pressure did increase, but it didn't go up that much. The dynamic pressure as defined by NOAA is particle density times the square of the speed. And the particle density is generally the proton, the solar wind is protons and electrons. So that's what we're measuring. Okay, so the CME was seen by the SOHO Solar Observatory, and then the ACE satellite saw it a little bit later. And then what happened, of course, is the K indices became elevated. That's the mean of Canada K indices. And once a CME passes the ACE satellite, it takes 30 minutes to an hour for that shock wave to hit Earth and register on our magnetometers. And you can see the elevated K indices went up pretty good. The highest was a K index of 8, which is up there. So what happened to the ionosphere as a result of that CME is shown in the lower right plot. That's the 3,000 kilometer F2 MUF over Dyess Air Force Base in Texas. And you can see that on the days previous to the CME and the days after, that the MUF was up there pretty good. But on the day that the CME hit us, the MUFs were depressed. So that's a good picture of tracking a CME all the way from the sun to its impact on the ionosphere at Earth. Now, W4ZV, he set a single-op 10-meter record in 2001. And what he planned to do is make another run at that in 2002. Unfortunately, that CME that we tracked resulted in pretty poor propagation to 10 meters. And you can see that in his rate plot. The dark vertical bars are 2001 when things were quiet. You can see his rates were pretty good for the contest period. The open bar is 2002, and that's when the CME affected the ionosphere, and his rates were well down. So he didn't even get close to breaking his own record. If you'd like to read more about the details of this event, they're in the March 2003 issue of CQ. Okay, so is there a way to maybe get a real-time view of what's happening to the F region when a CME hits? There kind of is. On the left is a plot of not only the A index, sunspot number, and also the solar flux. And there was a CME on September 30th, 2002. You can see the A index went up. That's the result of CME annotation. The right side of the plot is the end of September. And on the right is a plot of the effective sunspot number that comes from the Northwest Associates website. Yep, I did include that. That's good. Now, what the effective sunspot number is, basically the SSNE uses an F2 model of the ionosphere, and what it does is varies the sunspot number that's input to that model to force the model to agree with real-time ionoson data. So in a way, you have a real-time picture of what the ionosphere is doing. Now, this is the fit is attempted on many worldwide ionosons, so it's not a perfect fit. There are error bars that can be looked at here on the Northwest Research Associates website, but it does give a pretty good real-time indication of what's going on based on a geomagnetic storm. So if you want to take a look at that, just head to that URL, and also the July-August 2003 NCJ has more on the effective sunspot number parameter. Okay, let's track a solar radiation storm. That's the S in the GSR summary. Unfortunately, I don't have any log data for that one. That's because solar radiation storms affect the polar cap, and it's hard to get data, contest log data, with easily at least. But here's a solar radiation storm that was seen by the GOES satellite. It measures proton flux. That's the Geostationary Operational Environmental Satellite. You can see the proton flux went up on May 23rd. What happened was there was a big flare that caused a lot of protons to be headed towards Earth. The next measurement we see is a rheometer that measures cosmic ray absorption in terms of absorption in dB. You can see on that May 23rd when the proton flux went up, that caused more absorption at the rheometer in Frobisher Bay, which is up north. And what that rheometer does is just monitors noise at 38.2 megahertz. And when there's a lot of protons come in and cause more ionization down low in the D region, there's more absorption and the signal strength goes down, and that's calibrated in terms of dB of absorption. So you can see a nice little spike there. And what happened to the ionosphere because of that solar radiation storm, we can look at that from the ionosonde at College, Alaska, which is up in the polar cap. You can see that the instrument gave good MUF readings until May 23rd, when the protons caused so much D region absorption that the ionoson couldn't see the F2 region, so there was no data there. But we do know that there's a lot of absorption. You know, the F2 region is still there, of course, but it's just that there's so much absorption going through the D region on the vertically incident ionoson that they can't see the F2 region. So what would have happened is if we would have had an over-the-pole path on, even 20 meters or even maybe 15 meters, we probably would have seen that path suffer. Okay, the next one is radio blackout. That's the R in GSR. And what we'll take a look at is the contest log of ZF2RR. Now, we can't track a radio blackout because we have no warning of them. The radio blackout is caused by electromagnetic radiation from a solar flare, and it arrives at the same time as our visual indication of the solar flare, since they both travel at the speed of light. So, you know, if we visually see a flare, well, then it's affecting the ionosphere at the same time. And this is the rate for ZF2RR. Dan was doing a single band 10 meter low power, secure worldwide CW in 2000. And you can see, of course, 10 meters being a daylight band. You can see his rates were up in the day, and of course he was sleeping at night most of the time. You can see some pretty obvious dropouts, especially on the first day at the 18 to 1900 UTC hour. And what happened there was an X 1.9 flare, which is a pretty big flare. It happened at 1836. It caused excessive absorption on the daylight side of the Earth, and 10 meters dropped out for a bit. Now, on the second day, another even bigger flare happened at 1638 UTC, and you can see his rate went down in the 16 to 17 UTC hour. So that was not good for Dan, but it happened. Interestingly, he had two other obviously low rate hours that don't seem to fit, but talking to Dan and looking at his log, what he was doing there was looking for multipliers. There were no flares, but it was towards the end of the contest, and he made a conscious effort to leave rate and go look for multipliers. Now, one of his Dan's goals was trying to break the North America low power record. Unfortunately, he didn't make it. But if we extrapolate his results and assume that there weren't any flares, he probably would have broken the record. And all I can say here is it couldn't have happened to a nicer guy. And at that time, John ZF2AM was also doing a 15-meter band effort, and I should have captured his log, but I didn't. More than likely, we would have seen some of the same effect for him, too. Okay, summary. GSR, that's what you need to remember. G is geomagnetic storm. Geomagnetic storm is caused by CMEs and coronal holes. CMEs are most prevalent around solar maximum, whereas coronal holes are most prevalent on the decline of a solar cycle. So what that also says is the ascent of a solar cycle is generally pretty quiet. So we're still going to have some quiet times here until cycle 24 really starts nearing its peak. The S is solar radiation storms, also called polar cap absorption events, PCAs. They're caused by energetic protons from big solar flares, and they're most prevalent around solar max because that's when solar flares are most prevalent, although a solar flare, of course, can happen any time, but they're just more prevalent around solar maximum. And a radio blackout is caused by electromagnetic radiation at X-ray wavelengths from big solar flares, causing excessive D region absorption. And since they're tied to flares, they are also most prevalent around solar maximum. To summarize the impact of these three disturbances in order of least impact to the most impact, radio blackouts are probably probably offer the least impact to our amateur radio operations. Although there isn't any warning, they're usually of short duration, maybe an hour or two. The lower frequencies are impacted longer, and it only affects the daylight side of the Earth. You saw from ZF2RR's log that things cleared up pretty quick, so that puts them in a not too big of an impact compared to the other ones. Now the solar radiation storm is the next one up in line. We do have a couple hours warning because these are relativistic protons, and they do take a while to get here. At least we can tell that something's going to happen and maybe plan accordingly. A solar radiation storm can last a day or two, and it only affects the propagation across the polar cap. So how much of an issue that is can be a flip of the coin, I suppose. The biggest impact is the geomagnetic storm. We generally have a day or two warning because the shock wave travels not real fast, 600 to maybe at fast ones 2,000 kilometers per second. A geomagnetic storm, of course, can last for days, and it affects a much more widespread area, the high and mid-latitude ionosphere, both day and night. So in general, we want GSR ratings to be 1 or less on that scale of 1 to 5. Are all geomagnetic storms bad? No, they're not. VHFers, of course, love them, and it's pretty well documented that gradually evolving storms driven by slowly increasing southward IMF can even increase the nighttime low latitude F region ionization. So there could be positive impacts from a geomagnetic storm, and I think I bet you most of you guys could come up with examples of that stuff got better right before a storm. So there's good and there's bad. We just take what we get. Okay, review of auroral oval images. I bet you most everyone's seen those pictures that comes, they're generated by the Space Weather Prediction Center, and they're at that URL. They're called, loosely called PMAPs. The first P stands for power, and that's what the satellite estimates as the total power into the polar area from precipitating electrons due to geomagnetic storms. Once the satellite measures that, it compares it to one of 10 canned pictures, and that's the colored picture you see there superimposed on the map of the Earth. So it's not a real-time picture in the sense of it's presenting the real-time measurements of the satellite. The satellite summarizes its pass over the pole and then pulls one of 10 canned pictures that fits best. You can see the satellite track in that picture. It's going from the bottom to the top, and the black dots and the solid black lines perpendicular to track indicate the electron energy and the electron flux, respectively. The detector measures particles up to about, electrons up to about 20 kilo electron volts. If you look in some good ionospheric text, you'll see that an electron with 20 keV of energy only gets down to about 100 kilometers. And it's those electrons at 100 kilometers and above that cause visible aurora. Now, the higher energy electrons that get down to the D region are not measured by this detector. They roar right through. And so these pictures really don't tell us directly anything about absorption or auroral E. Now, the colors of the canned picture, what it indicates is where visible aurora is likely to occur. And that's a pretty important point. The orange just indicates that there's a high probability of aurora, and that's because the flux is very high. In other words, there are a lot of electrons getting in there. So where are the problems really when you look at one of those PMAPs? What we have here is a comparison the same night, the same time, an evening in the Midwest of one of the PMAPs and also a photo from the Defense Meteorological Satellite Program. You can, I think you can probably see my cursor, but here's Hudson Bay here on the right. Right down here at the bottom, you can see the lights of Minneapolis. There's Lake Superior. And if you look real hard, you can see the same features on the P-map. There's Hudson Bay. Minneapolis is right there. It's kind of obscured. But you can see that just because the P-map shows lots of orange in the auroral oval, that doesn't necessarily mean that the auroral oval is really full of ionization. You can see on this night, at least, that the extreme ionization was in bands, generally at the equator edge of the auroral zone. So don't make the mistake that just because you see a lot of orange means that there's this ionization all filling up. Again, that's a canned picture that statistically says where visible aurora is likely to occur, but what we're really interested in is the electrons that are much more energetic than the detectors on that satellite measure, the ones that get down into the D regions and the lower E region. And these Defense Meteorological Satellite Program pictures can show where the problems really would be. So the takeaway here is really that the auroral zone is not necessarily full of ionization that degrades HF. And of course, these would probably give VHFers some lots of good aurora-type contacts, because those are very bright, means that there's lots of ionization down at lower E regions and also down in the D region. So that's it. It's a short one tonight. And of course, this presentation will be on my website without audio, so go listen to the one at the PVRC webinar website. And just tonight I volunteered to do another webinar on 160-meter propagation in mid-September sometime. Tentatively, Ken and I agreed to December 16th, but I'm sure he'll publish that. So if there are any questions, we'll open it up for that right now.
Yep, very good. We will, Carl and I will firm up the date and time, but as he said, it looks like December 16th we'll do on 160, and the information will be announced on the reflectors and the normal places, but keep an eye on the PVRC webpage as well. So as far as questions go, as we mentioned in the opening, you can either type in something in the questions box and hit send and send it to us. Or if you'd like to speak directly to Carl and you have a microphone connected to your PC, what you need to do on the little rectangular grab tab is click on the raise your hand icon, and what I will do is unmute your mic, call on you, and you can go ahead. So come on, folks, don't be shy. Go ahead and fire away a couple questions here. And while we're waiting, Carl, I am surprised someone hasn't done this already, but typically people are with the contest coming up this weekend with sweepstakes and next weekend with CQ Worldwide. If you have any thoughts on those, maybe as far as what we might have for conditions.
Okay, well, first of all, Milton asked if I had seen an article, and I'll go look at that. Milton, could you pass along what your call is? Your email address is interesting, and I wonder what you do for a living. If you can get on or send a talk message or whatever.
Yeah, you can just go ahead and type that back in the questions pane,
okay.
And then what I'll do is I'll pick that up, or I can forward the question to you, and you can get that.
Okay. Okay, well, yes, Sweepstakes Phone is coming up this weekend, and then, of course, the weekend after that will be Worldwide CW. Well, with the recent solar activity, I think things are looking real good for 15 meters. And if the activity even increases some more, we may see some better 10-meter conditions. You know, 15 meters is still quite a long way. 21 megahertz is still well below 28, but it's conceivable that we may have enough solar activity to at least give us a little tantalizing hint of what's to come here in the next year or so. I expect the low bands will probably be real good. Again, we're in a at the bottom of a solar cycle, and usually things are pretty quiet geomagnetically speaking right now and for the next year or two. So the low band should be really good, and it would be nice to have all 6 bands available throughout the 48-hour period at certain times, at the appropriate times. But, the only one that's iffy is 10 meters, but who knows? We'll just have to wait and see how things progress.
Yeah, I was fortunate enough in CQ Worldwide Phone to grab 2 Europeans on 10 meters, and that was about it. So, and I'm going to be sitting out CQ Worldwide CW this year, which is killing me. But
Yeah.
it was interesting too during Worldwide Phone, just how awful the first night 80 and 160 were from here. It just was pretty bad. So, okay,
well,
go ahead.
We got warm weather up here, and of course that generally that can mean problems with thunderstorms and QRN. So we'll have to see what happens.
Yep. Okay, let's go ahead and try this. I see he had his hand raised and took it back down, but Luke, down to Brazil, Papa Yankee 8, Alpha Zulu Tango, let's see here once. Go ahead and try it. Are you with us?
Okay. Good evening, Paul. Nice to talk to you guys. Well, congratulations for the presentation. I'm very interested with this because past 2 years or 3 years we got amazing conditions on low band. Usually operate on near the equator line, but yes, down here we have blackouts and disturbance that you described on your presentation. My question is, how long we be in peace with the sun since now, okay?
In other words, you mean how long is the solar minimum period bit?
Yeah.
Okay, well, if we assume that, what I've done is assume that solar minimum is when the smooth sunspot number has gone below 20. And that happened in February of 2006. The past previous 5 solar min periods have seen us spend about 24 months at a smooth sunspot number of 20 and below. Now this solar min looks like, well, we're past 3 years right now, and it looks like we'll probably ascend through a smooth sunspot number of 20 in February of 2010. So this solar cycle, this solar minimum period is very unusual. It's about twice as long as those minimum periods that we've seen in our lifetime. Now, having said that, if we look at all the historical data, it's not very unusual. There have been many solar min periods that have lasted longer than what we've seen. So the sun really isn't doing anything unusual. It's just highly variable, and we don't have a lot of sample points. You only got 23 right now, so because we have 23 solar cycles. So did I answer your question, Luke?
Yes, thank you very much, and congratulations. Okay. I'll be here.
Okay, well, I hope to work a PY on 160 because I've never received a QSL yet from from any of the ones I've worked.
We gonna running on 160 with a great antenna. We have now full size log, full size loop for 160 for the CQWW contest, and we did on the best CQWW SSB we did about 60 counters and 25 zones on 160.
Well, congratulations. That sounds great, and hope to hear you on in a couple of weeks here.
Yes, that's very good, and thank you for joining us. Okay, let's take a couple of other questions here, and all right, looks like Scott's getting ready to go back down to Chile here. Maybe K0 Mike Delta is wondering, how does propagation look for the southern hemisphere?
Hey, Scott, how you doing? Oh, he's not on the mic. Okay. More than likely, if the recent solar activity continues, it'll probably be better than what I told you a couple weeks ago. I would definitely pay attention to 10 meters. I don't remember if you're doing all bands or just 20 meters, because you talked about a 20-meter Yagi, I remember. Probably you're going to do all the bands, because I know your daughter's going with you, so I'm sure she's going to have fun. But I'd keep an eye on 10 meters as long as the sun keeps doing some good things for us.
Yeah, and I think I may have been mistaken. It looks like he's maybe down there already, so he's joining us from Chile.
Oh, okay.
Okay, Peter, W2CDO, Carl, which models of solar physics best model the sunspot cycle?
Well, if one of them, well, that's a really loaded question. No one's predicted a sunspot cycle yet, really, so I'm not sure I could claim anyone. Which one is best? Well, I would hope that what we learn at this solar minimum can be input into the dynamo models that the solar scientists are coming up with and revising. I don't know how to answer that. Other than that, I don't think any physical model has really given us anything to write home about yet. But as we learn more and more from each solar cycle, unfortunately it takes 11 years, I think the models will get better, though.
Okay, Howard's wondering how far along the cycle would you say we currently are, and cycle 24. Go ahead.
Okay. Well, it looks like we're just starting to come out of solar minimum. Okay, it's the end of 2009. The ramp up of 24 appears to be following the NOAA prediction right now, and the NOAA prediction says that we're going to have a maximum smooth sunspot number of about 90 in 2013. So we're just right at the ascent of 24. That's what it looks like. Hopefully the sun won't, have all this activity and then go into an extended quiet period again. Of course, then everything's going to get delayed. But if we assume that this recent activity is going to continue, we've got another 3.5 to 4 years to the peak of solar cycle 24. And then, of course, we'll start descending again.
And you did a webinar on cycle 24 a couple of months back, I believe that was, which I imagine a lot of the information in there is still fairly pertinent, although it looks like we're seeing a few more spots since that time, so that may be worth going to watch too.
Yeah, that at the time I did that webinar, things were looking bleak. Since then, it looks like solar activity has picked up, so there seems to be a more positive sense to all this right now.
Okay, what is the reason the bottom of the solar cycle has been extended? You have any thoughts on that?
Oh, wow. There's been a theory that there's a jet stream in the sun that just has taken a longer time to get to the critical latitude to start producing spots. But as far as that theory goes, I'm not sure anybody knows why that took so slow. I just don't think anybody understands the physics of the sun enough to answer that question with any confidence. That four-letter word that starts with S, S happens, and we got caught in one of them apparently. Again, it's, like I say, this is what we've experienced here is not unusual when you look at all 23 solar cycles in recorded history. It's just very unusual over our lifetime, and we got used to very short minimums and some pretty good maximums. And more than likely, big maximums aren't going to happen for several more solar cycles. I think we're going into a smaller solar cycle period for
you know,
several decades probably. That's what the data suggests.
Okay, you may have just pretty much answered this next question from Jeremiah, since this cycle appears to be on the uptick a little bit, wondering how big you think the solar max will be. And again, I guess I would, you covered this in that Cycle 24 webinar. I don't know if there's anything else you want to add to this, Carl.
Well, all I can add is, the predictions say a maximum smooth sunspot number of 90 in 2013, but of course the sun could do anything, and we still could have a big cycle. It's just not very likely, but it still could happen since we just don't understand the sun that well in relation to solar cycles.
Yeah, the other webinar I'm referring to that Carl did, if you actually go to www.pvrc.org and click on the webinar link, the previous events we've had are all archived there, and he did one on Cycle 24, and it's got a lot of good information in, so you may want to go check that out. And I recall you kind of covered, hedged your bets there too, just because this is not an exact science yet, and anything could happen, but there's a lot of good information there. Okay,
yeah.
We're going to go back to Brazil. This is a question typed to us from Flavio, PY2 Zulu X-ray. Carl, what about 6 meters? Do you believe next year we'll have a great period for F2 on the magic band?
Probably not next year. If it's going to happen, it's going to happen near the solar cycle peak. If indeed this solar cycle is smaller than average, which is what it's predicted to do right now, any F2 openings on 6 are going to be kind of few and far between. Of course, I'm generally talking about North America to Europe type stuff. Since you're down in Brazil, you'll probably still have some good trans-equatorial propagation into the Caribbean. But generally, I think it won't be as extensive as it was like for the maximum around cycle 22 and 21. It'll probably be there, but just not as much as in past solar cycles. And like I said, we're going to have to, it's still too early for that, I think, at least for North America to Europe type stuff. That's what's good about the equatorial ionosphere. It's very robust, and even at solar min, there's some pretty good muffs, and trans-equatorial propagation is still a good possibility on 6 meters.
Okay, last call. Any other questions? Anyone want to speak directly to Carl? If you want to do that, click your little hand icon, and we'll go ahead and put you in touch with him. Okay.
Did you hear from Milton?
Yes, actually, I forwarded that to you, so you can open
did?
up the questions box. There's
okay. So I got to find the question box, right?
Yeah, find that back. Okay, David asks, how accurate are predictions today? And I'm not quite sure if this just refers to the how exact the science is, or but I'll take a stab at that.
I'll take a stab at it. Yeah, sure. Well, let's talk about two predictions. I don't know if you're asking about how accurate are solar cycle predictions or how accurate are propagation predictions. Well, I think probably propagation predictions are, I think you could place more confidence in them because I think we have a pretty good understanding, at least when the geomagnetic field is quiet. Solar cycle predictions, there's still a lot of way to go here. In the previous webinar, I think I showed a graph of that there's over 50 predictions for cycle 24. With that many predictions varying from very low to very high, that says we don't understand how the sun, what the processes in the sun are to generate solar cycles. So we're taking our best shot at it right now for solar cycle predictions. But like I said, I think propagation predictions, when the geomagnetic field is very quiet, I think are pretty accurate, as long as you understand that they're statistical in nature and not absolute. And if you understand that, well, that was another webinar about how to, how our propagation programs were developed and how do you use them. So let's go back to the PVRC website and take a look at that.
Okay, and then he was also asking about the reliability of contest predictions. And I think a lot of that probably has to do with where you pick those up in, because the magazines typically carry it, but those predictions are done a couple of months out to get them into the publication, and the ones online are probably a little bit more up to date.
Yeah. Let me go back to a plot here that I showed.
And Milton has his hand up. If I could just ask you to hold on, Milton, we'll get to you next.
Okay. Here's the plot of the maximum usable frequency over the Millstone Hill ionoson. Now, prior to that region 1029 rotating into view, the solar flux was pretty constant, and there weren't many sunspots. So you can see the variability of the ionosphere without any real solar influence. So again, that's why our prediction programs turned out to be statistical in nature, because they're trying to describe basically what you see in that plot is the daily variation that does not correlate very well to the daily sunspot number or daily 10.7 centimeter solar flux. So the predictions for Seek Your Worldwide CW, again, like Ken said, they were made early on because of the lead time of like a magazine or something, and they might not, if anything, they're probably going to be a little bit pessimistic because this recent solar activity could make things a little bit better than what the predictions say.
Okay, let's go ahead and get Milton on with the group here. Milton, go ahead.
Okay. Hi. Wonderful seminar, by the way. I've enjoyed it immensely. I have to tell you, I only got my license just a few years ago, and I thought this particular topic was amazing. Not just because of communications, which, by the way, is very important, not just for amateur, but for also professionals like pilots, but also it affected us directly when we had the big solar flare that or CME that actually took out pagers. Half the pager system of the United States went down. I thought that was interesting. Why in the world did that happen? This and how could they tell? This was a wonderful class. I wish I'd had it back then.
Yeah.
But
yeah, it's interesting that our little amateur radio view of disturbances, solar disturbances, is not the real important thing. What's really important is the hazards to astronauts, satellites that are up there that are very vulnerable to all the disturbances that the sun puts out. So it's really interesting that there's airline pilot. Airlines are started flying over the pole in I think about '92. Of course, that's the shorter route, uses less gas to get to over to like China and Japan, etc. But the problem is if there's the geomagnetic disturbances or even a solar radiation storm affecting the polar cap, they lose communications above, I think it's something around 80 degrees north latitude, because they usually talk with satellites that are over the equator. So if they have these disturbances that they cannot contact ground, they have to alter their course and not go over the pole and save money. And it's pretty huge savings when you can fly these over the pole pass. That is a really fascinating. Of course, the airline personnel can be exposed to a lot of protons too. Very energetic stuff up there if they don't watch it, and they have probably have limits and warnings and all kinds of stuff imposed on them.
True. I'm about to teach my first class, amateur radio class, and I was curious, out of all of this material, if you had to choose something, what would be the most important thing for them to know, realizing that techs mainly want to get into either the handy talkies or just the 2-meter, and then maybe work their way down to getting all the privileges. What would be the most important thing they should know about this?
Well, I think the most important thing probably would be just a general view of how a solar cycle affects the HF bands. And that can be summarized very nicely that in general, solar minimum is good for the lower bands. At solar max, that's a necessity for the higher bands being, 15 meters, 12 meters, and 10 meters, and even 6 meters to a certain extent.
Mm-hmm.
So if they just have that good general picture, that's probably a good start. And then if they get interested in other stuff, you can always branch off and go into details.
Well, that's great. Thank you very much. I appreciate it.
You're welcome. What's your call?
KD0 HGK. That's Kilo Delta Zero Hotel Golf Kilo.
Okay. What's the LIDAR stand for in your email?
LIDAR?
Yeah.
Just what it stands for in meteorology.
That's what I thought. Okay. That's what I thought. Kind of caught my eye. Okay.
All right, thank you, Milton. And along with what Carl suggested, it's good because if you're new to amateur radio and the HF bands and you're playing around with your radio and you wonder why you go to 10 meters or 15 meters, and hear anything. I mean, when I got started, I think in '77, I was like, boy, there's nothing on these bands. And then, one day, 10 meters starts coming to life and 15 meters, and so it just at that level it kind of explains what's going on. Okay, last call. Any other questions, folks? Go ahead and fire them away, otherwise we will wrap this up. All right, don't see anything else coming in, so why don't you give the presentation roll back to me.
Okay.
And we'll go ahead and finish this up.
Let's see here. Whoops. Close the wrong thing here. Change. Okay, change to Ken. Yes.
All right.
There you go.
And there we are. All right. Well, Carl, thank you once again for taking the time to put together the presentation and to be here with us and share all this information. It's great, and I know we take a look at the statistics on our webpage for some of the other webinars, and these are always quite popular. So thank you very much for taking the time to do this.
You're welcome, Ken.
And as we mentioned, we're talking about doing one on the 16th of December. I'll make the announcements, but along with that, just keep an eye on the PVRC webpage under the webinar link for upcoming events, as well as events like this that have been recorded. They will get posted there. So you'll be hearing, we've got a couple others that we're working on as well, so those will be put out once the dates and times have been firmed up with the presenters. So thank you for all who've joined us, and it's great to have the folks from Brazil and other parts of the world on here as well. That's what we're looking to do, is get as big of a reach as possible. It's a little bit difficult to do with so many time zones, but to the best extent we can, so we try to schedule these and hopefully bring in as many people as possible. So once again, thanks for joining us. Have a great weekend, folks. And for the contesters in the U.S., we've got sweepstakes this coming weekend, and then the rest of the world, CQ Worldwide CW. So I hope to see you on then. Take care, everyone. So long. Bye-bye.